Yeah, sure. Sounds good. Well, thanks. I appreciate the invitation. I want to express my gratitude to the Society for having me here today. Happy New Year to everyone. I suppose that it's still early on enough that we can say that. It makes sense. So today I want to give sort of a broad overview of work that I've been involved in over a number of years. It's not really a focused talk on a specific project more than it is like sort of an overview of some themes for mathematical modeling of oscillation that I've been involved in. Of course, the subject is much larger than myself, and I've made only modest contributions here to this area. So let me start by sort of reminding we're talking here about so there's really going to be two parts to this talk. I'll split it into one-dimensional models and two-dimensional models. Really, as far as applications to mathematical neuroscience and neuroscience more generally are concerned, these are reductions of high-dimensional, complicated models for neural oscillations. But of course, the high-dimensional models, even if they're easy to state in terms of mathematical equations, have a very complex structure and are not necessarily readily analyzed, particularly not through rigorous analysis and theorems and such. I just want to remind the audience there is a sort of a standard reduction tool that we use, which is the reduction to phase oscillation when dynamical systems find themselves near a periodic orbit that is sort of stable in terms of hyperbolicity criteria. So it sort of sucks in a neighborhood of the phase space. In that context, usually this is a context-specific reduction because it kind of depends on the specifics of the model that the reduction is coming from. But there's a way to model this sort of periodic phenomenology, not just by assuming that one is on the periodic orbit itself, but in a full neighborhood of the periodic orbit. So it sort of becomes a tool to try to understand when the model in question is close to this periodic structure, what its behavior would be. There's this idea of variable sensitivity to a stimulus, which is kind of like an instantaneous derivative relative to stimulus size that would affect how the frequency changes away from a natural frequency of oscillation to sort of a higher or a lower frequency, depending on whether there's excitatory or inhibitory stimulus present. Here we're talking about specifically, I want to focus on a very simple scenario that's been studied extensively in the 80s in particular. It's the type 1 oscillation paradigm, which means that this variable sensitivity to stimulus is positive. What that means is that the stimulus always results in an instantaneous increase of the natural frequency, right? So when one looks at a single oscillator's dynamics, sort of in very crude terms, one has this crude linear approximation at the bottom of the page here, essentially indicating that there's a natural frequency and then there's an added term that is a perturbation away from the natural frequency. And this perturbation is, there's the stimulus that is modulated by this phase-dependent sensitivity function. And so the setting that I'd like to talk about first is one where we're trying to sort of look at a cartoon, very idealized scenario where you have kind of like an extended system of these sorts of units. And the idea is that this system is unidirectional. Everything is extraordinarily homogeneous. So you have identical phase oscillators with the same identical frequency. You might as well call it one. and they're just talking to each other in a chain in a feed-forward connection, and there's a stimulus presented to them at the front end, which is the thing that's called theta zero here. It's just a straightforward periodic function that is ejected at the front end. And the idea here is that we're taking this crude approximation that I was talking about before, we're applying it in sequence. So an oscillator here hears with this variable sensitivity depending on its phase, the stimulus that is presented to it from its left neighbor directly, right? So it's just kind of a straightforward feed-forward chain, right? The model equation is downstairs. I'm going to refer to this model equation as this POFFC abbreviation just for the time being. And so now, in relation to this, right? So I've been involved in some numerical work that investigates for an idealized, this is called a phase response curve, right? This variable sensitivity to input, for an idealized type 1 phase response curve and a unimodal pulse stimulus. I've studied this sort of a system. The prior work here, Lysang Yang and I did some studies on low-dimensional attractors and these kinds of oscillator chains. These results were in particular indicative of two-dimensional attracting sets independent of the size of the system. And those results extended even when the homogeneity assumption was not necessarily at hand. So even if the coupling strength is dependent on the oscillator index, and also in the presence of certain feedback connections as well, right? So it's a very sort of broad, general phenomenology, not just for the simple, straightforward feed-forward setting. Also, later on, Oscar Lanford and I studied a particular category of phenomena that involve traveling wave structures in the idealized homogeneous chain setting. And that was sort of more careful mixture of numerical and analytical work. The phenomenology that I wanted to talk about today briefly is the following. So this is just a cartoon. I'll show you a couple of different simulations. The only way that these are different is that there are more oscillators in the second picture than they are in the first. But both of these are in the instance of this homogeneous feed-forward chain that is according to the model that I had just talked about. So the idea here is that if one starts time and runs with a straightforward uniform signal, the chain self-organizes into these sort of appropriate phase locking structures. So asymptotically down the chain, there's this approximate phase lock that the oscillators are entrained to, and this is like a time asymptotic phenomenology, right? So the larger system features the same phenomenology. Of course, the transients take a longer time to wash through, and actually my movie isn't even necessarily complete here, but it's just to indicate that there isn't anything quirky about the size of the system eventually, independent of the system size.
So may I interrupt you just a few seconds?
Yeah.
So can you give us some more information? So you have a forcing at the left, right?
There's the forcing at the left, which is the injected signal. I'm showing you a simulation where it's just forcing with frequency 1 periodic stimulus, right? So it's the It's the simplest periodic forcing that
Yeah.
you could present.
And then what's the network topology, how the cells communicate one
The
with each
network
other?
topology, so that's the feed-forward chain model.
Okay, all right,
Homogeneous,
all right,
right?
all
So
right,
there's
all right.
uniform coupling between each pair
right.
of neighbors going forward, and yeah, and it's the same phase response at each site, and it's the same structure of the stimulus.
All right, all right. Okay, thank you.
So, yeah, sure. So then, like, one sees something like this in a simulation. The question is how to capture it mathematically. This isn't particularly deep, right? So evidently, it's actually not a phase shift, phase locking. It turns out that the system is entrained to, but it's rather a time shift or a time delay lock. So there's essentially there's an asymptotic dynamic that is captured through some sort of periodic phase function, and then the neighbors are related to each other via a time shift of some sort.
Just
that is yeah.
is your so in the theory that is it is finite, or you let it go to infinity, the chain network?
It's independent of size, actually.
Okay.
Right. So for arbitrarily large, I mean, in infinite, this, fine, but you would still gonna want to measure for n when n is large, right? I mean, that's what
Okay.
infinite means numerically. And
All right.
This asymptotic phenomenology means that if you go sufficiently far down and wait sufficiently long, then the phase variable approximately looks like a time shift of the preceding neighbor. That's the idea. Does this make sense?
Yeah, thank you.
Yeah, with a periodic phase variable, right? And the phenomenon is not just an artifact of a particular choice of coupling strength that persists for a range of such. It's not there's nothing special here. The idea here being that altogether, it seems like if S is huge, and once one waits sufficiently long, the phase variable seems to satisfy an approximate delay differential equation that has this structure. The sort of further mathematical formulation here is you look at a delay differential equation in this context where theta is a circular phase variable, and the idea is to look for periodic solutions to this sort of a delay equation. Is there a period value, and then within that interval of between the period value, there's some sort of time shift, so that the equation in question would feature a solution pair. The theta tilde here is a function, and the alpha is a number that's between 0 and tau, right? So the idea here is that numerics are indicative of this kind of a solution structure, and in fact, they're indicating that this doesn't just happen for one value of the period, but that there's an interval of periods for which this is possible. But in particular, one of these periodic solutions attracts the dynamics of this uniform forcing signal, even though the uniform forcing signal isn't itself a solution to the delay equation, which is something that is sort of clear from the get-go, that the delay equation couldn't possibly be satisfied by the uniform forcing signal itself. So this is an interesting sort of phenomenon, because it indicates that one doesn't have to only force with something that's already perfectly solving the system, but there's actually some neighborhood in function space of forcing signals that would entrain the dynamics this way. And this is sort of the way to capture, right? So there's a collection of initial conditions. There's a collection of forcing signals that would that would allow for this kind of entrainment. In particular, the uniform forcing signal is one of them. And numerically, this seems to be something that's prevalent for various initial conditions. It's not a matter of cooking up special initial conditions. So that's what I mean when I say traveling wave in the context of this particular problem. For traveling wave, what we mean is that there's a shape solution, which is a phase function, and that then you have a traveling wave means that you have this structure where the sites evolve according to some kind of time translate of the wave shape. What we've done here is we've gone into the problem of searching for traveling waves in this context. There's obviously these natural questions that are theoretical in nature. Are there traveling wave solutions? Are they sort of asymptotically stable? So this is Lyapunov stability in that sense. Obviously, what that means is not entrainment only for the special initial conditions that are prescribed according to the traveling wave profile, but if one were to start with initial conditions that were coming from a broader basin, would there be entrainment toward this traveling wave profile? How large is the basin of attraction? Are there input signals that produce stable traveling waves despite not being solutions to the delay problem? So in particular, the numerics seem to indicate that's certainly the case, because forcing with this uniform frequency forcing function does produce this traveling wave entrainment in this asymptotic sense, despite the fact that it's not a solution to the delay equation. So that's the sort of this line of work that I've been involved in, is sort of investigates this kind of structure. The work that I did in particular with Oscar Lanford involved solving numerically this delay differential equation. There's actually a tight numerical methodology for solving problems like this in the context of searching for periodic solutions to the delay equation. There's an extraordinarily stable numerical algorithm that is iterative, where one can start with something that's an approximate solution and produce solutions that are a list of successively better approximations to the solution numerically. So this we did, and then for the resulting numerical solution, what we did was we tested the stability based on the assumption that the forcing signal was that particular type of numerical solution to the delay equation, and we of course discovered some stability properties there that we were able to leverage to show that the traveling wave profile produced by such a stable shape is actually globally Lyapunov stable. The result here in the context of this phase oscillator chain is actually very strong. It's a codimension 1 stability result, which is to say that for almost all, in the topological geometric sense, for almost all initial conditions, one has entrainment toward a traveling wave profile when the injected signal is itself a wave shape. This doesn't necessarily give first principles explanation for why this sort of model would feature stable traveling wave shapes in the first place. right? Because
Excuse me, Stan.
yes, mhm.
Just Aziz has a question, so.
Sure. Yeah, I'm sorry. Yeah, it's hard for me to track questions at the same time
Yes,
as Tom. So please feel free.
I'm sorry, Stan.
Yeah.
Because I'm more or less lost. That's why I'd like to make
Sure, sure.
something more clear.
Yeah.
I assume first of all, the definition you gave for the traveling wave looks quite similar to the notion of periodicity. What is the nuance exactly, please? First, second, assume that we have traveling waves. What does this mean for you in terms of application in neural dynamics?
So to answer your first question, right? The definition of traveling wave that I gave, let me just go back to that real quick. There's no particular nuance here. It's just I'm stating it so that it's clear what I mean when I say traveling wave. But basically, what it is there's a formula for a phase evolution, and you know, when you take that as the formula at a particular site, and then you consider a collection of its translates appropriately cooked up, the system co-evolves in a perfect fashion, so that at each site, that's the solution. At each site, the solution profile, right? The solution profile is such that at each site, the phase evolution is governed by the original phase shape appropriately shifted in time. So that's what this means. S here is the space variable, right? So the third oscillator has a phase variable θ3 of t. What does that mean? That means that to compute θ3 of t, you compute the wave shape at t plus 3 copies of alpha, where alpha is a shift. Right, so there's a time shift that you implement, and that is like that you can then compute according to whatever you want to be. So there's nothing particularly special here. That's just a way to capture it precisely, what it is that we mean. Now the consequences for this, I mean, first of all, just straight up, what are the consequences for this phase oscillator chain itself, right? So if we interpret these oscillators as essentially these simple dynamical units, the only thing that they do is they scream when they cross a particular firing threshold, right? Then what this would mean is that the entire network here, that is just a chain, is entrained so that they scream in sequence. So it's boom, 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 right? It's like it's a particular kind of pattern, an entrainment that is sort of, it's more general than a phase shift, right? So a phase shift would imply a time shift synchronization, but this is like a time shift synchronization. They're time shift synchronized. So if oscillator 2 is screaming at time 5, then you expect that oscillator 3 will be screaming at time 5 plus alpha or something like this, right? And that's the idea. The idea here is that there's this sort of periodic structure that despite starting with a completely disorganized chain, right, where the oscillators are probably screaming whenever because they started with various initial conditions. So from the get-go, for the time being, they're screaming randomly. But what happens is they sort of entrain to this a dynamic where they're screaming in sequence according to this pattern. Does that make sense?
Yeah, thank you. Merci pour ces éclairs.
Yeah. So yeah, please interrupt me.
Just a quick comment.
Sure.
Very quick comment for the neuroscience application. So they observe, as you know, because we discussed with some guys who do measurements in the brain. So they observe these waves in the brain. So it depends on the scale. But you have this kind of waves in the brain where it's exactly that. I mean, at the conceptual level. So it's kind of periodic, but there is a phase shift, and they observe that in the brain. Of course, it's not for all the time, but for some periods. And people are trying to make a signature or a mark of the. Is that when the brain is functioning well, or is that when is a stroke? So there's things of going on, and the measure of these brain waves are a very, very ongoing topic of research. So I think what you're showing in these theoretical models brings some theoretical stuff that are interesting.
So the idea here change like a cartoon for a spatially extended system, for like a tissue, right? And so you have this like cascade of a firing cascade, right? And the idea is that because of the way that these things are coupled to each other and communicating with each other, you really get a cascade that is sort of structurally organized after some time, and that's a feature of the network dynamics. It's not something that is yeah. So yeah. So you have another question?
I'm sorry. Normally we don't have to cut you.
Sure.
Anyway, just a very short question, related question. As you talk about synchronization, it seems that it is more a comment than a question. It seems that chain topologies synchronize very hardly, because your topology is a chain, as you said. Synchronization phenomena, Benjamin knows that because we have some work on. When the topology is like a chain, it is complicated to make the model to synchronize. Is it your case?
Well, so yeah, I mean, I should say, but I'll start by saying this is not a synchronization in the sense that they're that everything is at the same phase, but they're co-evolving periodically. And there's a periodic phase space here.
Yes.
That's what it is, right? There's a periodic phase space. So what happens is that they're all going to eventually be where the others were prior to them, right? The only question is whether they're doing random stuff, and what's happening here is that they're in training so that they're all covering the same dynamic in precisely the same order, right? They're co-evolving essentially, if that makes sense. It's a co-evolution in time. So from a mathematical perspective, right, there's this question of how does one arrive at a rigorous explanation for the existence of stable solutions to these kinds of delay equations, right? That's an interesting question, and sort of the numerical studies that motivated this line of work themselves can't answer a question like this. This is a mathematical question. Another mathematical question here is, there is this idea that the chain dynamics entrain in the way that I've described independently, or not independently, but they entrain despite not necessarily being forced by one of these perfect wave shapes, right? So despite not forcing with a perfect forcing function, asymptotically in space and time, there is this entrainment or this sort of traveling wave phenomenology. So there's this interesting other question about how large in function space, how large is the set of forcing functions that one can work with that may depart from perfect solutions to the delay problem and yet entrain the system in this way. That's an interesting question. So that in order to get at sort of some mathematical insight into this, something that we did was to simplify. So this is work with Bastian Fernandez. We sort of moved to a mathematically simpler model rather than this sort of smooth model that we had started with, in order to try to investigate from first principles the existence of solutions to the delay problem. What that means is we've gone to a piecewise affine model where really the phase-dependent selective hearing as well as the stimulus are really 0 or 1, and that makes for a much simpler dynamical equation that makes the problem sort of computationally tractable from first principles. One can impose this structure and then try to investigate from first principles how to solve the delay problem. This simplified model is just a 3-parameter model. There's the supports of these phase response and stimulus functions, and there's also the coupling strength. Aside from that, it's a sort of straightforward setting. In this context, we were able to establish a couple of theorems. One of them being that there's actually a collection of parameters in parameter space, a full sort of interval set, where one can solve the delay problem for various choices of these 3 parameters, and that in particular there is uniqueness when it comes to fixing the period of the solution for which one is looking for the delay problem. And among various things, right, when one looks at this particular solution, which is a stable solution in the Lyapunov sense, then that stable solution attracts almost all of the initial conditions for the system, right? But this is under the assumption that the forcing is with perfect wave shape to begin with. This is the first of the 2 results that are sort of readily established in the simplified setting. The second one chases this other problem, which is supposing that the system is forced with something that is not perfect in terms of solving the delay problem. What about that instance? Like, what happens to the
sorry, Stan, just one question, but I think it's interesting to keep people very understanding this stuff. So basically, in my idea, you have 2 kinds of coupling. One does not allow complete synchronization, meaning that, for example, you worked on that, you have one, it kicks the other, so you cannot synchronize because there's a delay. And the other one, some solutions might exist, which is you have complete synchronization, meaning that at the end of the day, all the oscillators are the same value, and you have a periodic solution, but constant in space. And you have also coexistence, also this type of traveling waves where you have a delay, but it's not that the coupling prevents the first solution. And I didn't get what does your system here allows for the system in some case going to a constant solution in space or not. You have you cannot have that because you have a delay in the coupling.
You can't have that here, yeah. So here the entrainment that is occurring is in large part due to the periodicity of the phase space, right? So because what's happening is you know, if one oscillator is kicking its front neighbor, it's not really possible that the 2 are going to co-evolve, right? There's
right, so
it's
one directional. That's
yes, it's one directional, and yeah, it's a chain, right? It's
yeah, but you could also sometimes you can also that asymptotically you have they synchronize. I mean, so of course it's at the limit. They are all the same, not without. So you could theoretically get that. Even it's.
I mean, it seems difficult to do, right? Because you would want you would have to have the signaling oscillator, it would have to be, yeah, I mean, it's difficult to imagine exactly that scenario because you have the signaling oscillator that is kicking the one that's in front of it. So that means it has to be receiving a stimulus at the same time, right?
Hmm.
It's, yeah, so,
Yeah,
so,
I see. Maybe we could discuss that later.
yeah, I think it's challenging to,
Yeah. Okay. Thanks.
to do that in this system, but, anyway, so what I was gonna say is that this is sort of the, ground level up result that essentially confirms what the phenomenology that was observed in a smooth system numerically. This is sort of established in this piecewise affine model where things are computationally tractable, right, from first principles. And then there's this other result, which is about the related problem, the problem where one is due to force the system with a shape that isn't necessarily a perfect solution to the delay equation, and despite that, right? So if one looks at the wave shape that is stable, it's actually stable also in the sense of function space. There's some neighborhood in the function space of forcing, phase functions that could be used as a forcing, not solutions to the delay equation, but nevertheless forcing functions that entrain the network toward the wave that is dictated by the wave shape that they're close to, right? So this second result sort of addresses to a certain extent the original question that we had started with regarding this phenomenology, that you're forcing this chain with this uniform frequency signal, and it finds itself entrained to some traveling wave that isn't necessarily generated by a uniform frequency wave shape, because uniform frequency wave shape doesn't even exist. It doesn't solve the delay equation. Right. So let me, at this point, let me move on to maybe the second part of the talk, because I've been talking for a while about the one-dimensional reduction phase oscillator systems. So maybe I'll skip ahead here just so that we don't run out of time, if that's okay with everyone. And if people have questions about how the results are established or what techniques might be involved, I can address those maybe afterwards. So I'll move to sort of the second thing that I wanted to discuss today in this overview, which is somewhat more sophisticated models, right? So phase reduction to phase dynamics is sort of a very crude tool for studying oscillations. It's actually not universally applicable. It only applies when, as far as neuroscience is concerned, when a neuron is in a oscillatory regime, or where a lot of these neural models, they feature bifurcation point in terms of dependence on parameters. This bifurcation sort of separates qualitatively two different regimes: the oscillatory regime from a regime where the neuron might find itself attracted to a stable equilibrium that it would never depart from unless it was presented a stimulus, right? So this is sort of like excitatory regime as opposed to the oscillatory regime, right? So in particular, when not excitatory, excitable, I think I misspoke. In the excitable regime, things are qualitatively different, and so another line of investigation is to try to understand network models where the interacting units are in this excitable regime prior to oscillation, and require an injection in order to complete a full oscillation and undergo a depolarization, right? So all this sort of second line of work starts with a similar reduction, but not as crude as the one that I started with first. The Hodgkin-Huxley equations are essentially a way to capture cable dynamics, but in a sort of physiologically relevant way. So in terms of something that's motivated by the actual structures in the nervous system. But obviously the original model that was proposed by Hodgkin and Huxley is extraordinarily complex. One can implement it, of course, and work with it numerically, but mathematical understanding, if one were to couple these with cells, complete mathematical understanding is still beyond reach. So one way that we proceed here is reducing, but maybe in a less crude way, when the dynamics are still present some sort of lower dimensional stable structure. The thing that I want to focus on for this part of the talk is the Fitzgerma reduction in particular. This is a category of models that stand as simplification of the original Hodgkin-Huxley equations. They are still complicated, possibly. In particular, there's a partial differential equation reduction to the original Hodgkin-Huxley model, but it's simpler in terms of its dynamics. It's sort of a two-dimensional system of PDEs with a spatial dependence that's based on a heat Laplacian term. The essentially this category of models have been used substantially over several decades as more mathematically tractable, despite featuring a complex range of phenomenology that is physiologically relevant, that is observed in applications. There's a lot of examples here. I hardly in a position to enumerate all of them, especially under time constraints, but I'll just mention a couple of lines of work here that are of particular interest to us. One of them has been this particular application that was used by folks at University of Washington to model axon damage in cells that are subject to concussive brain trauma. That's one line of work in which these sort of nonlinear models were implemented to provide for a setting where one has ability to understand how sequences of signal sequences of spikes might be transmuted when they are propagated across a medium that is like a neural axon, except that it's undergone damage. So it's a phenomenon referred to as focal axonal swelling. It's a widening of the cell axon body, which produces a variable transmission capability. And this line of investigation in particular has produced some evidence that some complicated nonlinear phenomena can occur in this setting. In particular, spikes can be lost from the sequence of from the signaling sequence. So there can be spike deletion or frequency adaptation on the basis of this kind of irregularity that is based on this kind of injury. So just to mention a couple of papers here that Benjamin's been involved in, specifically concerning this model in particular, that are sort of interesting contributions. So he has some work here on attracting sets and propagating bursting oscillations, as well as Hopf bifurcation analysis that we were discussing actually a little bit earlier today. The place where I'd like to take this next is the following. The theme in the first part of my talk was sort of looking at these unidirectional chains. I'd like to propose a similar sort of network model here, but instead of having these overly simple units at each of the sites here, I'd rather replace with cells that are themselves a little bit more complex. That here brings the model into this other category, which is the excitable systems rather than the oscillatory ones. The excitable systems are the ones that will be settling to a rest state unless they're provided with a sufficiently strong stimulus to depolarize. So here the model that we've looked at recently is a similar feed-forward chain that is homogeneous in nature, and but the idea here is that we're presenting a sequence of Dirac stimuli at the front end that it's a deterministic sequence, periodic. They kick the front site, and then each of these units is a Fitzgerma cell, and I will explain a little bit further what that means in terms of consequences here. But the idea here is that the front end, the first cell, is presented with this periodic sequence, and then everything afterwards is communication from the left neighbor. Every cell receives a Dirac kick from its left neighbor if its left neighbor undergoes a depolarization. So, in this context here, I'll clarify a little bit here what we mean in this model. The cells here are Fitzgerma cells where the nonlinearity is this negative leading coefficient cubic. And I'll explain a little bit more about the structure here. In order to have something that's a little bit more tractable mathematically, we chose to try to understand first what would happen if the stimuli were to be presented in the recovery variable. So this is something that will become clear in my next slide. The Fitzgerma model can be written as a two-dimensional model of ODEs, and where there's two variables, U and V. U is like to be interpreted as the original variable of interest, which is the voltage in the cell, as far as neuroscientific interpretation is concerned. And then this other variable V is like a recovery variable so there's a second order effect through a recovery variable that on the voltage. Yeah, this is sort of a summary of this model. So this is the model I want to talk about briefly here in the second part of the talk, just to make sure that everybody understands here the context. All cells other than the first cell are going to receive a stimulus from their left neighbor. The stimulus size here is the same as the size of the Dirac kicks that are arriving at the front end, and these stimuli are themselves Dirac kicks that occur when the left neighbor crosses a depolarization threshold, which we refer to as K here. It's a specific voltage variable amount that of a specific voltage amount that for numerical simulations one can just take to be 0. But yeah, so just a brief overview here to make sure that I remind folks about the structure of the Fitzgerma model. Essentially, what we have is a two-dimensional system where the UNITWIN is a graph in UV space. It's this cubic sort of for numerics. Of course, qualitative features of the cubic are the ones that we have in mind if F doesn't necessarily have to follow this formula, but the cubic is useful for doing actual calculations for this specific choice. The idea here is that in the isolated cell, the dynamics are as follows. So U is positive underneath the cubic, and it is negative above it, right? So U dot. So because above the cubic, V is greater than F of U, and below the cubic, V is less than F of U. So naturally, what happens here is if one starts the system at rest from the stable equilibrium and presents the system with a kick that displaces it from this rest state, then the system finds itself in a place where the voltage is going to tend to increase. There's slow fast analysis here that ensues. This is a slow fast system, so the geometric singular perturbation theory says if one puts together some critical trajectories that consist of following either the layer or the reduced dynamics, then one gets sort of a concatenation of idealized singular orbits. These are not the actual orbits of the system, but for small values of the parameter epsilon here, the actual orbits of the system are sort of entrained to this singular structure. So the red here represents an actual orbit of the system, and it follows approximately this trajectory. So the idea here is if this excitable Fitzgerma cell is presented with a stimulus that knocks it away from its rest state, it is then going to follow this smooth orbit, which is the red curve that was drawn here. And this smooth orbit is going to take it back to its rest phase. And it won't ever get there because this is a time asymptotic, but then does it stay close to the rest state? Maybe not, because it may be going to get kicked again. But if it never gets kicked, the dynamics are asymptotic to the rest state, right? So this is the sort of excitable dynamics framework, which is different from the oscillatory framework that I was talking about before. Yeah, please let me know if you have any questions here. Feel free to interrupt. I'm going to try to sort of move things along because I think I'm probably going to be short on time soon. Here, the idea that's important is the kick size plays a pretty significant role in whether there's going to be a depolarization or not, as well as the nature of the depolarization and exactly how long it's going to take for the system to find itself back close to the rest state. So if the stimulus size is substantial, there's going to be a depolarization and then a sort of this great trajectory that's going to take the system sort of approximately back to the rest phase. If the kick size is smaller, then there's an interesting phenomenology that starts to take hold where the orbit tracks this graph of the function f, it tends to hang close to this. It's a particular sort of structure that's present in slow-fast systems. In fact, if the kick size is even smaller, it could be the case that the stimulus isn't sufficient to induce a depolarization, which this is what this dashed line here represents, is a crossing of a depolarization event. The presence of a depolarization event. The polarization event might not occur if the stimulus size is too small. So what this means is if we chain a bunch of these things together, and then with the understanding that the stimulus the stimulus that comes from a left neighbor to the cell could occur at various points along its trajectory when it's not necessarily at rest, it sort of presents an idealized setting for studying cascades of depolarization, because in certain instances, a depolarization at one site may not necessarily induce a depolarization at the next site. Sort of things become complicated, depend on where the system is, on where the cell that is receiving the input finds itself in terms of its phase space. So let me just, as I'm probably gonna need to wrap up here. I'm very sorry. There's some standard parameter choices that one makes here to sort of bring the system close to an interesting state. The parameter choices that we've made are ones that provide for a sufficiently strong kick size that the rest, kicking from rest, will induce a polarization for sure. But at the same time, the kick size isn't so strong that the interesting folded geometry of this cubic graph, which is the critical manifold of the system in the language of geometric singular perturbations, we don't want that geometry to be obscured by the size of the kick, because a lot of the interesting phenomenology here happens when the stimulus size is sort of negotiated in between these two extremes of too small and too large. Some of the findings that just want to go over very briefly, and then I think we should finish, is things are sort of highly dependent on the periodicity of the injected stimulus, which is sort of a qualitatively different phenomenology from the phenomenology that one sees in the simpler phase oscillator setting. Here, what we have is when the forcing frequency is pretty low, there's this very simple dynamic, which is that a cell is forced away from the rest phase, and then it undergoes itself a depolarization and then returns rather close to its rest phase before it receives an additional stimulus. So what this means is that every site in this chain is going to basically follow essentially a pattern like this. And really, in this context, the phenomenology is very much like the traveling wave phenomenology in the phase oscillator system, right? So there's a cascade of depolarizations that is essentially time shifts of each other, and all of the cells are firing in sequence periodically. And in fact, the periodicity is in fact exactly the same as the periodicity of the injected sequence of kicks at the front end. Now, something interesting that can occur in this system is if a cell receives a stimulus and then the next stimulus arrives at a time when the cell is not yet sufficiently close to its resting phase, what can happen is that the system might not undergo a subsequent polarization directly after the next incoming stimulus, but might instead reset to rest without crossing the threshold. So what that means is that there's an effective period doubling phenomenon here. The injected signal is presented with a certain period, and then the first site that is receiving this injected signal is only depolarizing every second turn, for example. So that's what we refer to here as a simple mixed mode oscillation, because the system takes two turns, but in terms of the evolution of the voltage, but the voltage actually doesn't spike twice, it only spikes once. So effectively, if this is what's happening at the first site, the second site is seeing a sequence of of stimuli that has a period of 2 times the period of the incoming kick sequence. So this is sort of a richer phenomenology that this model presents here because of this slow fast structure in the individual cells, and it can get arbitrarily complicated. This is sort of the latest line of investigation that Benjamin and I have been involved in, which is kind of studying the complexity that can arise, in particular at specific values of the forcing period, where in fact this rich structure that the slow fast dynamics present when an orbit is close to the critical manifold allow for the sort of a high sensitivity to where the orbit is. So for example, this is the sort of thing that we've discovered, is that it is possible for the forcing period to be just such that forcing consecutively with that sort of a forcing frequency is going to produce a cascade of depolarizations, but then at some point the forcing, the stimulus will arrive too soon, and there will be a reset to the rest phase without a depolarization event. So in terms of the graph of the voltage, what that means is that there is a rhythm that features several depolarizations and then a quiescent phase. And what's interesting is how this sort of a wealth of additional structure here, because there's these Fitzgerma Google cells, actually results in a richer propagation of the oscillation. So, for example, forcing with a period that is rather low, which means that the forcing frequency is high, might mean that the first site loses some of the beats, and what that means is that the second site doesn't always see, doesn't actually see that same forcing frequency that the first site sees, but maybe sees half of it. So these are the sort of these are the other kinds of phenomena that are prevalent here. So essentially, that's kind of what I wanted to relay in the second part of this talk, is just the idea that there's a way to introduce further complexity here and bring the system closer to what's more mathematically, neuroscientifically interesting. And but there's a wealth of structure that emerges there, and some of that is very interesting and can provide for a lot of actual mathematical work in the future. So I think here I should stop. I'm sorry if I've gone over. This is just a few references that I have that the first of which, this is in reverse chronological order, the first of these is the one that sort of describes this second part of the talk in greater detail, and would provide some additional details about this interesting frequency modulation that occurs when the cells are excitable rather than oscillatory. Yeah, which is okay. So let me stop here. I'm really sorry. I think I've got someone over my time limit here. I was trying to do both of these sort of themes, but I might have been overly ambitious. I'm happy to discuss any details that I might have gone over too quickly, or also talk about some of the techniques. That would be fine, but I should stop now.
Thank you, Stan. Thank you for the talk. I think we have time for one question because yeah. So is there any question? We asked a couple of them. We interrupted you. So, but yeah, maybe we can have one or two questions if and then we could stop the formal session.
Yeah, sorry. In particular, I think I probably went a little too fast over the second part, but there may be some details there that may not be at people's fingertips if they haven't been working directly with these models. So if anybody has any questions about our choices or what we're focusing on, or how the phenomenology is sort of distinct from
Stan, please, could you go back to your model, Fidgeting model?
Sure.
I'd like you to make more clear the idea behind this model, this new model, when you are adding a sigma, this one, yes. You are adding a term here in the V equations. I'm sorry, because of my bad English, I didn't understand the meaning, the biological meaning of this term here.
So actually, this term, sorry to interrupt. The biological meaning here is not actually direct. This is a modeling choice that we made in order to bring the model to something that's a little bit more mathematically tractable. The original idea for these, right, is actually this PDE, and the spatial extension here, the coupling from between neighbors, is actually happening in the voltage variable itself, not in the recovery variable. So what we made is a modeling choice to move the coupling into the recovery variable because it made it a little bit easier to analyze mathematically. This is an admittedly artificial choice. So, a sort of a future line of investigation here might be to try to think of a different way to have the coupling be slightly more realistic, right? What we did is we said, what if the neighbors are communicating through their recovery variables, right? So in other words, one neighbor is talking to the other, the one that's listening is hearing by way of its recovery variable. It's a qualitatively different assumption, but it does make things a little bit simpler, right? Because in terms of the isolated cell, what it's saying is that all you have to do is see the coupling as an instantaneous, like if it's through a Dirac kick, as an instantaneous jump in the recovery.
Yes, clear. Okay.
Yeah. It's a little bit simpler. So this was Benjamin's idea.
Yes. I guess now. Okay.
I could add a comment. There's a bunch of other works. For example, actually in the PhD thesis of Mohamed Mama.
Yes. Okay.
Then the coupling acts. So the coupling acts on the not on the voltage directly, but on the conductances related. So the coupling is not on the voltage. So
yes,
by this, so it's another model. It's not the Fitzgerma PDE, but these networks, and there are a lot of people working with this kind of models where the coupling is not on the voltage directly, but on the other variables, which in this case have a real biological meaning. That's the
That's what we did with Mohammed.
yeah, exactly.
Yes, yes, okay. Thank you, thank you.
Yeah, it's an indirect coupling that is like a second order effect. So it's a little bit easier to understand, but it's a little further away from the original application that motivated it. That's kind of the trade-off.
Yeah, we could stop the formal the formal talk here. So thank you, Stan. Thank you again for this whole history and this new things. And thanks everybody for coming. Thanks for the SFBT to LMAH, and then thanks Stan again for this talk.
On peut applaudir, hein?
Yeah, it was a pleasure.
Merci beaucoup.